Welcome everyone. In this video I'm going to show you how to get the Schmid factor for a BCC phase from the Euler angles. And this is basically very similar to my previous video where I was doing the same exercise for an FCC, but since we have some differences between the two crystal systems or crystal structures, then I want to repeat the exercise for this particular structure as well. So let's start with the Schmid factor. What is that and why do we need it? So we want to represent the resolved shear stress in the crystal in a certain grain. And how we do that is basically we consider the geometry of the crystal in terms of the slip system. So we see which slip plane is active and which slip direction within that plane is active. And we also consider the stress acting within this slip system. So that's basically the essence of the Schmid factor. And I have this very bad drawing here, but what we have is that we have our in this case our single crystal, and you see that there are like three directions here. So we have the sigma, which represents the external stress expressed in terms of crystal, and I will tell you in a few minutes how to do that. And then we have this n vector, which is the normal of the plane and the selected slip plane that we are using for the calculation. And then the vector d is basically the slip direction within the plane n. So what we have here is basically two angles. One angle, which is in this case is phi, is defined between the sigma vector and the n vector, and the other angle, which is lambda, is defined between the sigma vector again and the d vector, so the direction. And then by using the cosine similarity, we can get the values of the cosine phi and the cosine lambda. So that's what you see here. And here you just see basically the vectors here put in the cosine similarity equation. And what you have here up here is dot product. So the dot product of these two vectors, which is basically the ith component multiplied by each other, and then it's summarized. So basically sigma 1 times n1 plus sigma 2 times n2 plus sigma 3 times n3. And then the product of this operation is just a simple number. So this is a dot product here. And then these, in this absolute value sign, is the length or the magnitude of the vector. So just magnitude, which is usually, let's say, this is a 3-component vector. So basically, in this case, the first component of the vector plus squared, plus the second component of the vector squared, and the third component of the vector squared. And then this also gives us a number, of course. And we repeat for this. But if you checked my previous video for the FCC system, then we knew that for this we could fix the number to square root of 3. Why? Because this represents the normal vector of the plane, which in FCC, not here in BCC, but in FCC is usually some 1-1-1 type of plane. Which means that whatever you do here, for example, you are changing the signs or something, this equation above here will always give you square root of 3. So we could fix that number in our calculations and just simplify the things. But here we have a problem, or not necessarily a problem, but here we have something different. So in this case, also in FCC we could fix this. Wait, I have to write this here. So in FCC we could fix this magnitude as square root of 2, because we always had something like 101 type of maybe like this, or maybe even it's more precise if we write something like this. So in FCC this could be fixed to square root of 2, because we always had the combination of these kind of vectors, and then if we use this equation here, then we always get square root of 2. But BCC is a bit different. Let me write that down. So the funny fact is that the slip direction, so this in BCC is a 111 type of plane, so not 111 type of direction, so it is not the plane like in the case of the FCC, because the FCC has the closed packed plane, but in BCC you cannot really talk about closed packed plane. But in BCC, instead of having this as the slip plane, we have this as a slip direction, and then there can be 3 different slip planes usually, and one is basically 110 type, and then another is 211 type, and then another can be 321 type. And each of these have different number of combinations or directions. So usually we say that here we have 12 combinations, 12 again with this, and here we have twice as much, so 24 different combinations. But what we wanted to see is that here, so in BCC, so the direction becomes this square root of 3, and then the normal, that is 3 different cases, and you have to be very careful about that all the time. So in one case, when we use this, then of course that's square root of 2, and then in the second case, then this is square root of 6, and then this is a bit more complicated, so this is 9 plus 4 plus 1, so this is square root of 14. So these are the 3 different options. So when you make these kind of multiplications, you have to be very careful that you really see which slip system is chosen, so which slip plane and which slip direction is chosen, so you choose the proper magnitude of the vectors. And then we check the d and the n values, but now let's talk about the sigma. So as I told you, we have a sort of stress which is represented within the crystal's coordinate system, and that is the sigma. So what is that? So basically, when we have a material, and let's say that is basically a rectangular specimen, so something like this, I cannot really draw it nicely, then we have its own coordinate system, so something like this, where let's say this is the y direction, and it's sometimes also called transverse direction, and then this is the x direction, which is sometimes called rolling direction, and then this is the z, or sometimes called normal direction. And then we assign the stress, or we define the stress within this coordinate system. And usually we say that if, let's say, this is a specimen that we subject to tensile testing, we usually pull it in this direction. So we make an elongation along the x-axis. And what it means in terms of coordinates, then that will mean that, let me just do it like this. So we have the x, y, z, and that means that the x is 1 because we do it in this direction, and then y is 0 because nothing is acting in this direction, and z is 0 because nothing is acting in this direction. So in this part we just use the 1, 0, 0. And of course, in this case, if we just have pure uniaxial stresses, then 3-component vector is just enough to define, let's say, a planar stress or like a pure planar stress like xy or something like that. But if you really want to have 3D stresses, then instead of this you will have a 3x3 matrix, and that will define your stress state. But here we have a pure uniaxial stress, and that is acting in the x direction. But this is defined in this coordinate system, which is the specimen's coordinate system. So the specimen's coordinate system is needed to be rotated to match the crystal's coordinate system, and basically the rotation between the two coordinate systems, the rotation operation, can be done through 3 consecutive rotations, and then these 3 consecutive rotations contain the Euler angles. So these Euler angles basically define that this much you should rotate in this direction, and that much you should rotate in that direction. And what you see here, this huge matrix, is basically the product of that 3 consecutive rotation matrices. So this is just a single piece of matrix. And what you do is that you take your stress that is defined here. You have your Euler angles. So first of all, you translate this matrix into numbers. So basically you just substitute the Euler angles into their corresponding places based on which is phi 1, which is phi 2, and which is capital phi. And then you have this 3x3 matrix filled up with some numbers, like yes. And then you multiply your vector, this guy here, this stress vector, you multiply it by the g, and what you get here is basically the sigma vector. So that's how we get the sigma. So you multiply your external stress, I don't know how to call it to not confuse you, but yeah, let's call it like S, so that is here. So the S is the stress represented in this coordinate system here, and then if you multiply it by the rotation matrix or orientation matrix, then you get your stress represented in the crystal coordinate system. So it's very simple. And then what we can do is, for example, we can calculate the Schmid vectors with this formula here, or basically these two formulas, because we also know, sorry for the confusing jumps between the different parts. So we also know that the Schmid vector is defined basically by this equation, so the product of these two numbers, this guy and this guy. So this is the Schmid vector. And then we assign a Schmid vector to each pixel on an EBSD image, for example. And here what you can see is that this is a duplex steel, which means that it consists of 2 phases, BCC phase and an FCC phase. And what I did here is that in the background, the gray parts are the FCC grains. For example, here you can see annealing twins, and that they only appear in FCC material. and in stills it's very nicely visible. So these are annealing twins, and the colored parts are the BCC parts. And what I did, I assigned the corresponding Schmid factor to the BCC pixels. So you can see that the two faces separate from each other very nicely. And if you check my other video, the previous one, for the FCC calculation, then you can clearly see the difference, because there I did the same. So I highlighted the FCC grains with the corresponding Schmid factor coloring, and then I had the BCC grains, which are now colored, with this gray coloring. And then that's a very nice contrast. So we got our stuff here, and all we have to know is that how did we get these numbers. So first of all, I show you my table, which I made for BCC calculation. Please check the description, and you can see a download link there for the table. And I just want to ask you to please subscribe if you use that table, because it just took some time for me to create the table and also to make this video, and you just have to do just a single click. So thanks in advance. So we check the table, how we do the mathematics, and then I show you this image with my software where I can click each grains, and we can tell what's the Schmid factor in each areas. So this is the table. It's not so complicated. So what we have here is that we expect the 3 Euler angles in degrees. So these are the 3 Euler angles. I just typed them in. I took it from the image. So this will be actually from a pixel of the image. And then first of all, we just convert everything into radians. And then based on that, we just calculate the orientation matrix. So here you can see the 9 components of that matrix. And you really have to take care of the numbers, in a sense that you have to make sure that if you use degrees, stick to the degrees across the whole work, and if you use radians, then use radians. I use radians here partly because the axis equation, for example, for the trigonometric functions, expect the angles defined in radians instead of degrees. But yeah, it's more convenient to see these numbers. So we have the orientation matrix, so we can move to the formulas where we calculate cosine phi and cosine lambda. So again, I just put the orientation matrix here, just we can keep our eyes on it. And then this is our stress direction. So as I told you in the introduction, we define the stress direction to be a pure uniaxial direction in the x direction. So basically only the x component is 1, the others are 0. And so we go from here, we multiply this vector, this 1/3 vector, with this 3/3 matrix, and then we get this guy here. So this is the crystal stress, so the stress represented in the crystal's coordinate system. And then we have this. So yeah, this is a huge mess, but what you can see here, I separated the 3 different types of planes. So here you can see the 101 type. Here you can see the 112 type plane. And these two big things are one part, so half of the 123 type, and the other half of the 123 type planes. I really hope that there are no typos in this, but if you discover some, just please let me know. And also if you know what's the error, then you can also highlight that as well. So let's just go back. It's highly possible that I made a mistake somewhere with the signs, or just, yeah, it's too much numbers. So we have the 3 components for the plane vector. So that was the n vector from the drawing, and using the plane vector and the crystal stress vector, we calculate the cosine phi, and then using the direction vector and again the crystal stress vector, we calculate the cosine lambda, and then we just multiply these two numbers together, and then we get the Schmid factor. And after doing this, we repeat the same strategy 47 times more, so that is here. And what I did here is I checked all these numbers and put the maximum value here in this rectangle or in this box. So that is basically what we have here. Is we took the maximum value of this set of numbers here, and I also did some trick here that I don't care about the directions, so sometimes it can happen. You can see it here clearly that one of the numbers are negative, so sometimes it can happen that these numbers are actually negative, but we just don't think about the directions here. We just think about the magnitude of the Schmid factor, so we don't care if it's stress in the tensile direction or if it is a stress in the compressive direction. So we just take the absolute value and then we take the largest one among these 48 different numbers. So that's what we get here. And this table, again, it's shared in the description, and I just expect you to subscribe in exchange for this table. So your subscription is greatly appreciated. So let's jump back to the pictures. So here we are. And now let's check the software that I wrote, and let's go through some of these pixels. First of all, let me highlight that I took a pixel for my Excel sheet demonstration from here. So I took the Euler angles of somewhere from here, and then if I go back to the table, then let's just check the value. So 0.483 or 0.48. We might neglect the last digit, but 0.483. So now I open the software and I just show the most important area from that window. So here is our image. You can see it's the same image as here. And then let's check this pixel here, because that was our concern. So I took the Schmid factor from there, and it was 0.483. So let's just click here. And you can see it's 0.481. So it was somewhere from here. If I start clicking around, then you can see that the last digit is changing slightly, or maybe not. Yeah, you can see that. It depends on, yeah, it was maybe this pixel, so 0.483. I haven't checked the exact coordinates. And you can also see that it is from the 1, 0, 1 plane and minus 1, 1, 1 direction. So let's jump back to the table and let's check where does this come from. So here is the table, and you can see the slip systems here, so the combination of the plane and the direction, and it's 0.483. So I will start to look for that value. So it is here, and 101 minus 111, 101 minus 111. So yeah, it's the same. So then we can start clicking around, and I noted down some values from taken from another software for the same material. And then this was a very funny place because it's so bright as compared to the other materials. So I was curious about the Schmid factor of that. So that should be 0.41 from the other software. So I click here and we see if it is right or not. It is right. And then I took something here that should be 0.45. So I just click here, 0.45. So this yellowish area is 0.45. And then I haven't checked the other values, but I'm pretty sure that this should be 0.5 almost exactly, because it's very dark red. So yeah, you can see it's 0.5. But the most important was this, basically these 3 spots, because I also checked them with some other software, which is more reliable maybe than this. But now we confirm that our values is good. Our values are good because it is matching the other software. So then I can click basically somewhere else or anywhere else, and I can just check what's the value here and what's the value there. But you can see that in general we have quite high Schmid factors, so everything is around 0.48, 49 something. Yeah, so some of the grains are not that high. But basically that's all. That's all about this. So what we did here is that we learned how to convert the stress defined in the specimen's coordinate system into the crystal's coordinate system. And that is basically the stress vector which is needed to calculate the Schmid factor by using the components. And we used this orientation matrix, and we used these 3 Euler angles to create the rotation between the 2 coordinate systems. And then we used these 2 equations to get the components of the Schmid factor, and then the product of these 2. So we multiplied each other, multiplied them with each other, and then we got the Schmid factor, and then we just put those values on a map, and then we could get everything. So this is how you get from the Euler angles to the Schmid factor values for the BCC system. So I hope that you learned something, and I hope that this video and the Excel sheet was somewhat useful for you. I think it can be quite useful if you are learning, for example, materials science or something, materials engineering. Then usually this is a typical homework or home assignment or exam question. So here you can follow it step by step, and hopefully you can also recreate everything, and then you can learn how to do this. And I strongly suggest you, not for this, but at least for BCC, because that's more simple, do all the calculations by hand, at least for one specific case. Then you get an idea about how this cosine similarity works. So you can do all the multiplications between the components, and then so on and so on. And you can check your calculations with my Excel table basically. So yeah, I hope it was helpful for you, and see you in the next video.